Today I'd like to talk about a really important application of diagonalization, which is taking powers of a matrix. Okay, so there are many reasons why we might want to take powers of a matrix. So multiplying a matrix by itself, some number of times, well, that's the same as composing a linear transformation some number of times. So applying a linear transformation repeatedly. And matrix taking a power of a matrix involves a lot of matrix multiplication, and matrix multiplication, as you know, is a pretty involved calculation, especially if the matrices get big. So it would be great if there was a very efficient way to take large powers of a matrix without having to do so many matrix multiplications. And we touched on this last time near the end of the lecture, but I just want to remind you what we said last time, and also we're going to do a couple examples. So first, let's recall from last time that we can take powers of a matrix very easily if the matrix is diagonalizable. So if some matrix A, and A is an n by n matrix, again, we're always talking about square matrices now. So if A is diagonalizable, what does that mean? Well, it essentially means then we can write A in this special form, where we have some matrix P, which we learned last time is the matrix consisting of, where the columns of P are the eigenvectors for A, a basis for the eigenvectors of A. And then we have a diagonal matrix D, so D is a diagonal matrix, and then we have the inverse of P. And recall, a matrix is diagonalizable when the algebraic multiplicities of all of the eigenvalues equal the geometric multiplicities. Okay, but yeah. So what is this P and D? So let me just write that in. So P has to be invertible, obviously, because we have P inverse there. And again, this comes from the eigenvectors. And this matrix D is a diagonal matrix. And the entries along the diagonal, as we saw last time, are the eigenvalues. We'll see that again in the examples we do. Okay, so what's the big idea? Well then, suppose we want to take a power of A. So A to, I'm calling A an n by n matrix. So let's say A to the k instead of n. So I'm taking some power of this matrix. Well, if we can write A this way, then this is just P dP inverse to the k, which is P dP inverse times P dP inverse, etc. It's P dP inverse. And what we noticed last time is all of the P inverse times P's cancel. And essentially we're just left with P times D times D times D n times. Okay, so it's P times D to the k, k times, times P inverse. And diagonal matrices are super easy to take powers of, because if D is, let's say this diagonal matrix, so I'll just call the diagonal entries D1, D2. Although again, in practice, these end up being eigenvalues when we diagonalize a matrix. And yeah, 0 is elsewhere. So yeah, if D is this matrix, then what's D to the nth power, or D to the kth power, I guess? Well, all you do is you take each of the diagonal entries to the kth power. And this only works for diagonal matrices. It does not work in general. It's not so easy to take powers. But there we go. So that's the idea. Let's do an example, since we didn't last time. So example. Well, let's find A to the power of 100. Where A is the following matrix. Minus 3, minus 2, that'll be the first column, and then 4, 3. Okay. Well, the idea is to diagonalize. So we're going to try to diagonalize A. How do we do that? So we have to first find the eigenvalues and eigenvectors. Okay, great. So we're going to look at, as we always do, the determinant of A minus lambda I. And we're going to set that equal to 0. And then that's going to tell us what our eigenvalues are. But yeah, what is this determinant? It's, well, first of all, it's A minus lambda I. Subtract lambda off the diagonal. 3 minus lambda. So the determinant of this matrix, which is, well, let me just write it out. So minus 3 minus lambda times 3 minus lambda. Remember, we have a nice formula for the determinant in a 2 by 2 case. Minus 4 times negative 2, so actually at plus 8. But this is, let's see, we have a lambda squared. And then we have a minus 3 lambda plus 3 lambda. That cancels. We have a minus 9 plus 8. So this is just lambda squared, minus 9 plus 8. So it's lambda squared minus 1. Okay, and then we're going to set that equal to 0. Set it equal to 0. Lambda squared minus 1. But it's factors, right? It's lambda minus 1 times lambda plus 1. And so my eigenvalues are 1 and minus 1. Okay, those are some nice eigenvalues. What do these eigenvalues tell me, by the way, about this linear transformation? Well, it tells me there's a vector, there's some vector, it's an eigenvector, that when I apply this transformation, it just ends up exactly where it started. That's what an eigenvalue of 1 tells me, actually. Right? It doesn't change at all. A times that vector just equals 1 times the vector. A times the vector equals the vector itself. Okay. And an eigenvalue of minus 1 actually tells me I have a vector, there's another vector I can find that it gets flipped around the origin. Okay, it's like a 180-degree rotation, or reflection, or something like that. Okay, so we can kind of have a picture of this transformation, but let's try to find those vectors. So we want to find the eigenvectors associated with lambda equals 1. In fact, it will only be one of them. How do we do that? Well, we just plug in lambda equals 1. So we have minus 3 minus lambda is, or minus 1 is minus 4. So we have minus 4 minus 2. 4, and then we have 3 minus 1, which is 2. This is exactly what we were expecting. We're expecting to get a matrix like this where the columns are dependent. Okay. Because we need to look at the null space for the eigenvectors, right? So do you see an eigenvector here for this matrix? Again, things in the null space of this matrix are ways to combine the columns to get 0. And I definitely see one. So let's call this lambda 1. V1 is going to be, I take one of the first column and one of the second column, and I get 0. So that's the eigenvector associated with lambda equals 1. And then for lambda equals negative 1, what's the matrix we're looking at? We have 3 minus negative 1 this time. Minus 3 minus negative 1. So it's minus 2, 4, and then 4. And again, we can just see an eigenvector by looking at this matrix. Take double the first column and add the second column, and we get the 0 vector. So there's another eigenvector. Okay, let's diagonalize. How do we do that? Well, A is going to be PDP, PDP inverse. So what is my P, my matrix P? It's going to have the eigenvectors as its columns, right? So here's my matrix P. My diagonal matrix is going to have the eigenvalues down the diagonal. And notice I had to put 1 there and minus 1 there because I chose to put the eigenvalue associated with 1 in the first column. So that 1 needs to go in the first diagonal entry, and the minus 1 needs to go in the second. But you could have swapped these two columns, and then you would swap these two entries. So diagonalization is not unique. I'm not sure if I said that earlier, but yeah, not unique. And then let's find the inverse of P. So the inverse of p was 1 over the determinant, so that's 1 minus 2, which is a negative 1, so I just have to make everything negative. And then I swap these two entries, but that doesn't really change anything. And I take the negative of the 2 and the 1 in my formula for the inverse. But then I'm multiplying by this negative 1 anyway, so I think this stays a 2 and a 1. Is that right? Again, yeah, I'm using this formula, so the inverse of a 2 by 2 matrix. It's good to just remember this formula. It's 1 over the determinant times dA minus B minus C. This is a formula that you'll get a lot of mileage out of. Okay, so hopefully I did that right. If I didn't do that right, it actually doesn't matter because look what's going to happen. A to the n is P dP inverse to the n, which is, like we just proved above, it's P times d to the, actually n is 100 here, right? But yeah, let me just put in an n for now. Or let me put in 100, because that's what we're trying to do. 100. P times d to the 100 times P inverse. That's the beauty of diagonalization. This becomes this. And what's d to the 100? So I'm just going to write P times this matrix to the 100. It's just 1 to the 100, 0, 0, and then minus 1 to the 100. But minus 1 to an even power is just 1. So actually what we get here is something really nice. It's just P times 1, 0, 0, 1, the identity matrix, times P inverse, which is P times P inverse, right? Because this is the identity matrix. And P times P inverse is, again, the identity. So apparently A to the 100 is the identity matrix in this problem. It's not always going to be true. But in this problem, this matrix, it turns out that raising it to the 100 power, you just get the identity. And you probably also could have solved this problem by doing a squared, a cubed, a to the 4th. Just calculating those out. See if you spot a pattern. And you'd be able to figure this out. But yeah, that's the power of diagonalization. So next thing I'd like to talk about is this is just a really, really cool application of diagonalization again. So it's the Fibonacci numbers. You've probably heard of the Fibonacci numbers before. But if not, I'm going to explain what they are. It's a really interesting number sequence. It comes up all over the place, even in nature. These come up in unexpected places. Maybe I'll show you one place that come up in a second after I explain what they are. But here's going to be our motivating question. So question. Given some sequence of numbers, so what's that going to look like? Well, I'll just call it A1, A2, A3, etc. Might be an infinite sequence. Yeah, can we find a formula for the nth element of the sequence? Okay, so that's an interesting thing we might want to do. Let's look at some examples. Let's start with a super easy example. 1, 2, 3, 4, 5. And of course, you don't know for sure it's going to continue like 6, 7, 8. Like maybe the next number is 27 for some reason. But imagine it's just the obvious sequence. What's the formula for the nth number? So if this is A1, A2, A3, etc., then an, the nth number, is just n itself, right? So A1 is 1, A2 is 2, A3 is 3. So that's what I mean, a formula for the nth number. Let's do a slightly harder one. What if you have 1, 4, 9, 16? Again, it's only slightly harder. So I'm sure you can see what the pattern is here. So yeah, what's the nth number? Oh, it's n squared. Those are the square numbers. Let me give you a slightly harder one even. Maybe this one's considerably harder. These are called the triangular numbers. 1, 3, 6, 10, 15. Next one is 21. And you might spot a pattern here. So like this is plus 2 and plus 3. and plus 4. So we see this pattern here, but maybe this doesn't help us so much to find an explicit formula, because I just want to say, tell me the 20th triangular number, and then you should be able to plug the number 20 into a formula, and it'll tell you the 20th number here, without having to add 2, 3, 4, etc. So how might we do this? Well, here's one very interesting way to solve this. So 1, this is why they're called triangular numbers. You can make them in a triangle like this. Okay, 1, 3, 6, 10 is going to be like this, etc. Right? Okay, and there's something interesting here that we can do. What if we take this arrangement here? Okay, so it's 10 dots. I already messed it up there. I should not have a dot right there. Can I delete that one? Yeah. So I'm going to take those 10 dots, but then I'm going to add this same arrangement right next to it, but flipped around. So see what I just did there? Flipped it around 180 degrees, fit those two pieces together. It makes a rectangle. So this is A4 that we want, right, that 10, but I have a 4 by 5 rectangle. Okay, and the area of that rectangle is just 4 times 5, which is 20, and I need to take half of that to get to 10. So I think we just found a way to get a formula. So what is, well, so if I take 2 times the nth triangular number, then I get a rectangle with dimensions n times n plus 1. So the area is, the number of dots is n times n plus 1, which means that actually an is going to be n times n plus 1 over 2. And this is actually a formula that works. So if I want the 20th triangular number, just an example of how I use this formula, A20, it's 20 times 21 over 2, which is 10 times 21, which is 210. That's very useful to have a formula like that. Okay, here's one more. So 1, 2, 4. Actually, let's start at 2 just to make it easy, or just to make it match up really well. So 2, 4, 8, 16, 32. I'm sure you've seen this sequence before. They're the powers of 2. But there's sort of 2 ways to write a formula. So here's the explicit formula. A to the n is just 2 to the power of n, right? So here's A1, A2, A3, A4, A5. 2 to the 5 is 32. So this is what I would call an explicit formula. But there's another kind of formula called a recursive formula. So that's a recursive formula. What is the recursive formula? That would tell us how we get one number in the sequence from the previous one. Okay, so and so that's kind of like this here. So we're saying, what's the pattern here? We're just always doing times 2, right? So an is 2 times an minus 1. That's a one recursive formula. That's the easiest recursive formula. Okay, so that's just to give you some idea of what the question is. Now I'm going to give you the Fibonacci sequence. So here's another example. So these are the Fibonacci numbers. It goes 1, 1, 2, 3, 5, 8. See if you can spot the pattern here. 13, 21, etc. What's the pattern here? I'm going to say what it is, but feel free to pause the video if you haven't figured it out yet. See if you can figure it out. So the pattern is, to get any one number in the sequence, you actually add the previous 2. So 3 plus 5 is 8. And 5 plus 8 is 13. And 8 plus 13 is 21. 13 plus 21 is 34. So the next one should be 34. Then the next one should be 55. Then 89, etc. So those are the Fibonacci numbers. Let's not call them A1, A2. Let's call them F1, F2. So this is a very special sequence. It's F3, F4, F5, etc. And so there's a recursive formula for the Fibonacci numbers, which is, to get any Fibonacci number, I just add the previous two. That's how you write it as a formula, right? So we get f5, or f6, that's the 8. I do f5 plus f4. See, this is just the index down here. So I do the previous index and then the 1, 2 earlier, and I add those. Great, so we found a recursive formula, so check mark. But then what about an explicit formula? Question mark, right? You can try to figure one out, but it seems very difficult. So I want something to, if I plug in the number 10, it should spit out 55, the 10th number in the sequence. Right? So again, if you'd like, you can pause and think about this, but I just warn you, it's very hard to come up with. But that's exactly what we're going to do. And we're going to do it using, surprisingly enough, diagonalization of a matrix. So, first of all, where's the matrix coming from? So here's our idea. So we're going to encode the formula, the recursive formula that we have. In a matrix. And here's how we're going to do it. So what do we do with matrices? Well, we multiply them by vectors and we get other vectors, right? The matrix, that's how a matrix represents the transformation. So here's what we're going to do. We're going to have a matrix here that I'm going to multiply by a vector and I'm going to get a new vector. What are the things in this vector going to be? Well, it's going to be the nth Fibonacci number. And then I'm going to put the one before also. So I'm going to have fn and fn minus 1. Now, if we know what fn minus 1 and fn minus 2 are, and now, so over here I'm going to put the sort of previous step. So instead of fn and fn minus 1, I'm going to put fn minus 1 and fn minus 2. And then so for example, I'll have 5, 3, and when I multiply by this matrix, I want it to give me 8, 5. I want it to sort of get the next Fibonacci number. And I'll need to, of course, keep track of the one before it in order to have any chance of getting the next one. Right? So that's why I have 2 entries here. Well, what should this matrix be? Well, let's look at the multiplication. Right? So if I do this one times that one, I should get fn. Right? So what linear combination do I want? I want 1 times fn minus 1, and then 1 times fn minus 2. Right? I just want to add those and get fn. So that top row is just going to have 1s in it. And then what about down here? How do I get fn minus 1 from these two? Well, that's kind of a weird question, right? Because it's right there already. So I just want to pick that entry out. So I just want a 1 times that plus 0 of this one. Okay, and so this matrix right here, this simple looking matrix, actually encodes this formula. So the idea is, so how do we use this? Let's show that it works. Let's say I have 2 consecutive Fibonacci numbers, 5 and 3. I'm going to multiply by this matrix, 1, 1, 0. And I'm going to get, 1 times 5, 1 times 3. That's 5 plus 3 is 8. And I have 1 times 5 plus 0 times 3, which is 5. So see, this matrix just gives me the next 2. Start with 3 and 5, I get 5 and 8. By the way, this is a good time to talk about how the Fibonacci numbers come up in nature. So actually, on the way to my office this morning, I picked this up. So it's a pine cone. And if you look at this part of the pine cone right here, okay, the base of the pine cone, doesn't look that interesting at first, but after a while you start to see these spirals. So what spirals am I talking about? Well, here's one. So if I start here, let's say here, and go this way, see how it spirals out? And then, so how many spirals are there? There's this one, and then there's this one, and then this one, and then this one here, and then this one here, and then we're back to the first one. Okay, so there are 5 spirals. 1, 2, 3, 4, 5, like that. Okay, and 5 is a Fibonacci number, but I mean that probably doesn't seem so amazing yet, because I mean 5 is in a lot of sequences. But here's what's really mind-blowing. So if you look hard enough, you can actually start to see spirals going the other way. It's kind of like an optical illusion. So what do I mean the other way? So not this one, but you're looking at the spirals going to the left. So this one. This is one of them here. So there's 1, and then 2, 3, 4, 5, 6, 7, 8. Okay, so there are 8 spirals. So again, 1, 2, 3, 4, 5, 6, 7, 8. And 8 is the next Fibonacci number. And it turns out that this is not an accident. Okay, so we did not just get lucky. If you go out and find a pine cone, and you do what we just did, you look at the base here, you'll see that there are 2 sets of spirals, one going to the left, one going to the right. And the number of each kind of spiral, it'll almost always be 2 consecutive Fibonacci numbers. That's mind-blowing. So this one was 5 and 8. You can also find pine cones where it's 8 and 13. I've seen ones like that before. Or you can find ones where it's 3 and 5. But you'll probably not find a pine cone where it's 4 and 7. So these are really fundamental in some way. So they come up in the most surprising of places. But in any case, what are we trying to do? We're trying to find an explicit formula for the nth Fibonacci number. And we are making a lot of progress because what can we do with this matrix now? Let's say I start with 1, 1. And then I multiply by this matrix. What should I get? I should get 2, 1, and I do. Let's say I multiply by this matrix again. What should I get? I should get the next 2, 3, 2. And then if I do it again, I should get 5, 3, and then 8, 5. So what's going on here is if I do 1, 1, and then I multiply by this matrix on the left some number of times, this is where the power of a matrix is coming in. So let's say I want to get to 8, 5. How many times would I have to multiply it by? Well, once will get me to, so let's see, I'm starting with F2 in the top space, right? And I want to get to F6. So I want to go 1, 2, 3, 4. I want to multiply it 4 times. So if I do this matrix to the 4th power, right, multiplying by it 4 times in a row, that should get me to 8, 5. Okay. So this one was F6, this one was F2. And so basically, if we understand how to take powers of this matrix, if we understand what the powers of this matrix look like, we have an explicit formula for the Fibonacci numbers. And so before I start trying to diagonalize this matrix and take its powers, I just want to let's clear this up a little bit. So we would love it if the 4th power of a matrix got us the 4th Fibonacci number. So what's actually pretty common here is you kind of extend back the sequence a little bit. So F0, well, what should that be? That should be 0. Maybe a 0 plus 1 is 1. And then what plus 0 is 1? 1. So I'll call that F negative 1, I guess. Okay, so if I start with that 0, 1, so that's F0. And then if I multiply this by this matrix 1, 1, 1, 0 to the nth power, what I should get is Fn up here. So it'll be Fn and then Fn minus 1 down here. Right? So the nth Fibonacci number is the top entry in the vector 1, 1, 1, 0, this matrix, times the vector 0, 1. Okay. Oh, but wait a second. So multiplying by 0, 1, and then looking at the top entry, well, what's that going to be? It's just going to be 0 of whatever this is, plus 1 times the top right entry in the matrix. And that's going to get me the top entry in the vector. So really what I'm after is, or alternatively, it's just the top right entry. The top right entry in the matrix 1, 1, 1, 0 to the nth power. So that's a really nice characterization of this. So literally all we need to do is figure out how to take powers of this matrix. We'll look at the top right entry once we are able to do that. That will be an explicit formula for the nth Fibonacci number. I don't know about you, but I find this really exciting because first time I saw the sequence, I thought, oh, there's no way you could come up with an explicit formula, but there is. We're going to do it. Okay, what's the idea? We're going to diagonalize this matrix. So let's call this A. So the idea is going to diagonalize our matrix A. Not A factorial, but let's diagonalize A. And again, first, we're going to find the eigenvalues and eigenvectors. I have to warn you, this matrix looks deceptively simple, right? It's just ones and zeros. You might think this is going to be super easy. It turns out it's extremely messy. The other thing is diagonalization is such a subtle thing because I think I told you last time that, I mean, this is actually the example I used, I think, of a matrix that's not diagonalizable. 1, 1, 0, 1. You cannot diagonalize that. But it turns out you can diagonalize 1, 1, 1, 0. So these look the same, but they're not. They're very different in terms of their linear transformations. So this one you can diagonalize. How do we do it? We look at a determinant of A minus lambda I. Just what we've learned. So that's going to be the determinant of 1 minus lambda, 1, 1, 0 minus lambda, which is minus lambda. And this is going to be 1 minus lambda times negative lambda minus 1, which is lambda squared minus lambda minus 1. Okay, we're going to set that equal to 0. And this cannot be factored easily. It does have 2 real roots, though. We can find them using the quadratic formula. So let's use the quadratic formula. So lambda is negative b, so it's 1 plus or minus square root of b squared minus 4ac. So it's going to be 1 minus a negative 4, so 1 plus 4 over 2a, which is 2. So this is 1 plus or minus a square root of 5 over 2. This is a very special number. And you might have heard of this number before. This number here, at least with the plus, is called the golden ratio. This number also comes up all over the place. In nature, for example. Yeah, I should be more clear. So the golden ratio, so it's denoted by this letter phi, this Greek letter. Let's call phi this root, 1 plus square root of 5 over 2. That's called the golden ratio. And I'll call the other one phi bar, which is 1 minus square root of 5 over 2. Right, so we have 2 roots. And these are our 2 eigenvalues. Right? So that's great. So these are the eigenvalues. Right, the roots of the characteristic polynomial. It happens that this has a special name. It's called the golden ratio. I'm actually going to use the symbol phi as much as I can to avoid having to write out this whole expression. So that's great. We found the eigenvalues. What else do we need in order to diagonalize this matrix? We need its eigenvectors. So we're going to find the eigenvectors. So let's start with lambda equals, I mean, they're not This example we did before, there's really nice integers. Here there are these really complicated expressions. So let's start with lambda equals the golden ratio. And what are we going to do? We're going to look at this null space. So we want the determinant of, or not the determinant, sorry, we want to look at the matrix 1 minus phi, 1 negative phi. Okay, we want a vector in the null space of this matrix. Well, how are we going to find that? Well, here's how we can find it. The fact that there is an eigenvector, okay, associated with this eigenvalue, means there's some non-zero vector in the null space of this matrix, right? Which means that this matrix is not invertible, which by our unifying theorem means that the columns are dependent. So this matrix, one of the columns should just be a multiple of the other. And we can see what that multiple should be, right? The second column is supposed to be, negative phi times the first column. So I think this is an eigenvector. I think an eigenvector is, if I just multiply the first column by phi, right, and then just add the second column, that's supposed to give me 0. Okay. But yeah, does it actually work? Well, let's try it. Right? I should be able to multiply this by this matrix and get 0. Okay, 1 minus phi times phi, that's, so top entry is phi minus phi squared plus 1. It's not looking like 0, right? And then how about down here? I get phi minus phi. Well, that's good. That is 0. Okay, but what about this top entry? I'm supposed to get 0, 0 if this is actually in a null space, right? But that top entry, okay, that looks suspiciously like this polynomial here, right? Remember, phi is a root of this polynomial. So phi and this phi bar, they both satisfy phi squared minus phi, phi squared minus phi minus 1 is supposed to be 0, right? And the same with phi bar. Phi bar squared minus phi bar minus 1 is 0. So actually this top thing is just the negative of that, right? It's minus phi squared plus phi plus 1, but that's also 0. Right? So this is actually just 0, 0. Nice. So this is in a null space. So this should be an eigenvector for the matrix A. Okay, so this is my first eigenvector. Phi comma 1, where phi, you remember, is this number. Okay. Similarly, here's my second eigenvalue. But you can basically just deduce immediately that, by the same logic, this should be an eigenvector as well. Okay, so this is going to be my V2. Because, again, when you multiply by this matrix, except with the phis replaced by phi bar, right, you're just going to get the same thing, but the phis are going to be replaced by phi bar. But we still have that phi bar as a root of this polynomial, of the characteristic polynomial. So you're going to get 0, 0. You should try it just to be sure. But yeah, this is an eigenvector associated with that. And this V1 is an eigenvector associated with this. So here's how we diagonalize, right? A, which is this matrix, is, what do I write first? I want to write my P. So this is A. I'm going to do P, D, P inverse. What is P? The eigenvectors are the columns of P. So I have phi 1 and then phi bar 1. Right? D, my diagonal matrix. Along the diagonal, what do I have to put? I have to put the eigenvalues associated with these eigenvectors. So the first eigenvalue is phi, right? That's associated with this eigenvalue, phi, this eigenvector, phi 1. Then my second eigenvalue is phi bar. Again, that's the one with the minus sign there. So there's my diagonal matrix D. What do I put here? I have to put P inverse, right? So what is P inverse? It's Well, let me leave some space. This is going to be more involved than I thought, actually. I have to do 1 over the determinant. That's 1 over phi minus phi bar. I'll try to figure out what that is. And then I'm just going to use that same formula I used earlier for a 2 by 2 inverse. Okay, so I swap these two, and then I need to put negative signs on these. Okay. Is this something nice, by the way? Like what is phi? Yeah, what is phi minus phi bar? Note that phi minus phi bar is, let's write out what it is. 1 plus square root of 5 over 2 minus 1 minus square root of 5 over 2. I have a half minus a half, and I have a square root of 5 over 2 plus another square root of 5 over 2, which is just a square root of 5. So phi minus phi bar is actually a square root of 5. So 1 over that is going to be 1 over a square root of 5. Again, it's times this matrix here. Okay. Yeah, so let's fill that in. Maybe I don't want to write the square root of 5 a bunch of times, so I'll just write that in as a scalar down here. Got 1 over the square root of 5 times 1 minus phi bar minus 1 phi. And again, what do I want? I want the let's remind ourselves. Where was it? It's the top right entry. It's the top right entry in this matrix A to the n. Okay, so let's calculate A to the n. Let me get a new page for this. I think we're almost done. What is A to the n going to be? Again, we're after the top right entry in this A to the n. Well, it's just going to be P dP inverse to the n. But that's P by, like the logic we used earlier, is P times just this D to the n times P inverse. So what's that going to look like? It's going to look like phi bar 1, 1 times D to the n. Here's what D to the n is going to look like. There's D. D to the n is going to be phi to the n, 0, 0, phi bar to the n. Nice. This scalar of 1/5, can we just do something with that? So that's part of my P inverse, I guess. All right, so, well, I'll just keep it here with the P inverse. Yeah, so I just write down P inverse. Okay. Now we just need a top right entry. And notice we're now just multiplying 3 matrices together. So it's going to be a little tedious, but let's just do it. We're going to multiply these matrices together. So this is going to equal, what's this one times that one? It's phi times phi to the n plus 0. And then I have a phi bar times phi bar to the n. And then I have a phi to the n down here, and then I have a phi bar to the n. Okay, that's the product of these first two. And I'll just rewrite the times 1 over square root of 5 times this matrix. And what is this going to equal? Again, what am I after? I'm after... I don't care what's here. Like there's something here, and there's something here, and there's something here. This is what I care about. I want this top right entry, because that's going to be my explicit formula for the nth Fibonacci number. And where is that going to come from? It's going to come from this times this. And well, let's put that 1 over square root of 5 out there. We can't forget about that. That's actually going to be really important in our final formula. Okay, so I have a phi to the, I can rewrite this as phi to the n plus 1 times phi bar, but I have a minus sign here. And then I have a plus phi bar to the n plus 1 times this phi, right? Okay. Is there any way to make this look any nicer? Well, yes. There's another relationship between phi and phi bar that we did not talk about. which is that phi, what is phi times phi bar? In other words, what is the product of the roots of this quadratic? It's supposed to be the constant term, right? So phi times phi bar is -1. So if I want, I can replace the phi bars with -1 over phi. And similarly, phi is -1 over phi bar. I'm going to do that because, see, I have phi to the n plus 1 times a phi bar. I'm just going to call that phi bar a -1 over phi. Okay, so this is actually phi bar is -1 over phi, so it's actually this phi to the n, right? Because the minus sign cancels. And I'm going to replace that phi there with this, -1 over phi bar. So this is going to become minus phi bar to the n. And then again, I still have stuff in these other entries, but I don't care about it. But I do have this 1 over square root of 5 out here. So now I'm going to multiply through that square root of 5. And I just found a beautiful formula for the nth Fibonacci number. If we did everything right, it should be square root of 1 over square root of 5 times that, which is phi to the n minus phi bar to the n. That's beautiful. So let me just box that. I mean, it is a complicated formula. Don't let its sort of simplicity fool you here, because phi is this number, right? It's going to be a pain to take this number to large powers, but still, we have a formula for it. Okay, and that's phi bar. Okay, so if we want the nth Fibonacci number, we want to take that number, multiply, take it to the nth power, that number, take it to the nth power, subtract them, then divide by the square root of 5, and somehow we get an integer, right? We get a Fibonacci number. All these square roots of 5 are going to cancel somehow and leave us with an integer. That's the really beautiful thing about this. Somehow everything works out right in the end. Can we do an example? So what is f2 by our formula? Well, actually, what's the actual f2? The actual f2 is 1. That's not so exciting. What is exciting is that somehow you're going to get 1 when you write this out. So 1 over square root of 5 times phi to the n. N is 2, so I need to do this to the second power. And then I need to do minus this to the second power. Okay, 1 over square root of 5, and then I have, what do I get in the numerators here? I'm going to get a 4 in both denominators, but what am I going to get in the numerators? I'm going to get 1 plus a 2 root 5 plus a root 5 squared, which is 5. And I'm going to get minus a 1 minus a 2 root 5 plus root 5 squared, which is 5. Wait, my parentheses are weird here. Oh, I shouldn't have one there. Minus 2 root 5. Yeah, and then I just have a 4 down here in the denominator, right? We can't forget to square that 2 in the denominator. Okay, what does this end up becoming? Okay, I have a 5 minus 5. Those cancel. And I have a 1 minus 1. Those cancel. What does not cancel is this. I have a 2 root 5 minus negative 2 root 5. So that's a 4 root 5. But I'm dividing by 4. Oh, this is so wonderful. That cancels, and then that cancels. So I get 1, which is indeed the second Fibonacci number. And this actually works. So you see what I mean? The square roots of 5 somehow cancel. And this actually works for any Fibonacci number. You can plug in 10, do this calculation, and you will get 55 in the end. So I think that's just a really wonderful application of diagonalization of a matrix when it's sort of least expected. So that seems like a good note to end on. So thanks for watching.